Okay, so the next topic is network function. Okay, suppose if you have some network, the network may consist of resistor, inductor, and capacitor. That will combination of that resistor, inductor, capacitor. We call it as a network. Then we give some input. Okay, that input we call it as x of omega, and then output is y of omega. Here the assumption is we are giving the input, that input is having some frequency and that frequency is variable. Okay, if you vary your input signal frequency, then what is your output signal? Okay, so again this network okay function depends on the frequency, because sometime it may allow some frequency or sometime it may not allow some frequency. Okay, based on that we'll be having the filter characteristics. And also one more thing, that input could be either like a voltage or current. Okay, and output also it may be like a voltage or current. So you may give input voltage, you may observe the output voltage, or otherwise you may give the input voltage, you may observe the output current, or in the reverse manner you may give input current or you may observe the output voltage, or otherwise you may give input current and also you may observe the output current. So there are uh, uh, variety of combinations are possible. So generally there are four combinations are possible. Okay, so once if the network is given, okay, that network transfer function, we used to write like omega h of omega. The transfer function of the network is h of omega, that is output divided by input, output divided by input. Okay, so the same thing we can also write like this: h of s is equal to y of s divided by x of s. Okay, the Laplace transform of the output divided by the Laplace transform of the input will give you h of s. Then once if you substitute s is equal to j omega, then we can get this transfer function. Okay, again depending on that what we are observing at the output and what we are giving at the input, there are four different definitions are possible. The one is first the voltage gain transfer function. That means we are giving the input voltage and also we are observing the output voltage. So first one is voltage gain transfer function. Okay, in general the transfer function, okay, in general the transfer function is h of s, but once if we use the voltage gain, we can write like g of s. That means this is output voltage divided by input voltage, output voltage divided by input voltage. Okay, so this is voltage gain transfer function. So next similarly we'll also have the current gain transfer function. Next, current gain transfer function. So that time this is g of s, output I naught of s, and then output current divided by input current. Okay, then and again please note down everything we are writing in the s domain. That means we are in the frequency domain. Okay, it is not a time domain equation, it is the frequency domain equation. So once if it is in frequency domain, then you can write like this. Okay, if it is time domain, you cannot write directly y of t divided by x of t and all. That is not true. Okay, you cannot write y of t divided by x of t like that. Okay, that is not possible. But only in the frequency domain you can write like this. Okay, either in the frequency domain or s domain. S domain is also a frequency domain. Okay, then I naught of s divided by I of s. And then the third quantity is transfer impedance. Transfer impedance. That means at the output we are observing the voltage. Okay, then in the input we are considering what is the input current. Okay, if it is output voltage divided by input current, then that we'll call it as a transfer impedance. Then fourth quantity is transfer admittance. Transfer admittance. Again here the transfer admittance means y of s is equal to, in the output we are observing current. Okay, input we are observing the voltage, then it is transfer admittance. Okay, in general Okay, out of all this quantity, most probably we'll be discussing about the voltage gain transfer function. Okay, mostly we'll discuss about the voltage gain transfer function. That means what is the input voltage, then what is the corresponding output voltage for a given system. So suppose if it is h of s, then y of s divided by x of s, then again the same thing can also be written like h of omega, then this is output v naught of omega divided by vi of omega. Okay, in general we'll write this quantity for voltage. Okay, so that's why output voltage divided by input voltage. Then this h of omega, okay, is function of omega, that we can call it we can write as a magnitude, and also with the some phase. Okay, with the some phase, with the some phase phi we can write. Again, please note down, this phase is function of omega, the phase. Okay, phase is function of omega. So once we have some equation, then we'll come to know what is exactly this, that pi phase. Okay, so the magnitude of the transfer function, the any transfer function can be written in terms of its magnitude and also with its phase. Okay, then what is the frequency response analysis? Okay, complete frequency response. That means the complete frequency response means what is the magnitude versus frequency. Okay, that means how this quantity mod h omega is getting varied with respect to omega. Okay, that plot we'll call it as a magnitude versus frequency response, and also phase, how the phase is varying with respect to frequency. Okay, so phase versus frequency, these two plots combined together we'll call it as a complete frequency response. Now we'll take a simple network, then we'll see what is the complete frequency response of the circuit. Okay, so obtain complete frequency response, complete frequency response. One resistor and capacitor, input plus vi, or C, this is output. Okay, this is simple RC network. Okay, and please note down, this vi is not a constant voltage, it is a AC signal with some frequency. Again, that frequency is variable. Okay, so what is the assumption here? Here this vi is AC signal with variable frequency, okay, then again you know that in Laplace transform domain, instead of C we can write 1 by SC. Okay, for a frequency analysis, 1 by SC, then this is V naught, this is input Vi. Okay, now we are again, what is the voltage, output voltage due to the input voltage, that we have to analyze. Okay, now again V naught is equal to, again simply voltage division, what is the input voltage, then what is this value, that value is 1 by j omega c, because s means j omega, 1 by j omega c divided by r plus 1 by j omega c. Okay, then if you make the adjustment, again this is vi 1 divided by 1 plus j omega rc, now you take the ratio of v naught by vi, then that we'll call it as a h of omega. H of omega value is 1 divided by 1 plus j omega rc. Okay, so h of omega is equal to 1 divided by 1 plus j omega rc. Then what is the magnitude? That is 1 by 1 plus omega rc whole square, overall square root. Then what is the phase? Pi is equal to minus tan inverse omega rc. Okay, now we are having both magnitude as well as phase of this transfer function, phase. Okay, now we can plot both magnitude response as well as the phase response. Okay, now you observe this function, magnitude function. Okay, so at low frequency, okay, when uh, see when omega, see observe here at this okay, when omega rc is less than 1, okay, when omega rc is less than 1, okay, then what is the meaning of this one? When omega rc is less than 1, or omega is equal to less than 1 by rc, okay, when you choose a frequency in such a way the frequency values are lesser than 1 by rc, then approximately, okay, approximately what is h omega, approximately it is 1. Okay, because this omega rc value is very very less, then approximately this is 1. Then but after some point, because you are keep on increasing the frequency, say if this is the frequency scale, again 0 to infinite, okay, so at some point, okay, this may be satisfied, but once if you keep on increasing the frequency beyond certain level, this term will dominate, this omega rc will dominate. Then once if this term dominates, say for example if omega rc is greater than 1, then what will happen? Okay, the gain will be less than 1. Then more the omega rc, then lesser the gain, because it is in the denominator. Okay, then what is happening? At low frequency the gain is constant. Okay, beyond a certain range, once the frequency if you keep on increasing, then the gain decreases. Okay, so at low frequency the gain is constant. So the plot will be something like this. So okay, at a low frequency, the gain is constant. Beyond certain frequency, the gain starts decreasing and goes to 0 like this. Okay, this is omega, and this is h omega, mod h omega, and this value is 1. At low frequency the value is 1 approximately. Once if you keep on increasing the frequency beyond certain range, then the gain will get reduced. Okay, then what about the phase? Okay, phase again, see if omega rc value is less, okay, if omega rc value is less, say for example, again suppose if omega rc is much much less than 1, then what would be the phase? Minus tan inverse of, if it is less than 1, say for example if it is close to 0, I can assume it like a 0, then it is 0. When frequency is 0, the phase is 0. But once if you keep on increasing the frequency, okay, say for example after certain time, this is having some value tan inverse of 0, then maybe tan inverse of zero point 0.1, okay, and the next tan inverse of zero point 0.2, like that it keeps on increasing. Then what will happen? The phase also will increase, okay, negatively. The phase also will increase negatively. At the extreme point, what is the possibility? The omega may be infinite. So once if it is infinite, okay, minus tan inverse of infinite is minus 90 degree. Okay, so that means your phase varies from 0 to minus 90 degree. Your phase varies from 0 to minus 90 degree. So what is the variation of the phase with respect to frequency? This is the frequency axis. Again, this is the phase axis. This is positive phase, this is negative phase. Again, in the beginning the phase is 0. Again, if you keep on increasing the frequency, the phase also increases negatively, but after a certain time it reaches minus 90 degree, minus 90 degree. Okay, so this is minus 90 degree. In the beginning, the phase is 0, it increases negatively. When the frequency is very, very high, the phase reaches minus 90 degree. Okay, so this is the magnitude plot, magnitude plot, and this is phase plot. This is magnitude plot and this is phase plot. Okay, sometime for the system analysis we need both. We have to concentrate on magnitude and as well as phase. Suppose sometime if your magnitude may be better, but if the phase is worst, then also we cannot use that frequency. So whenever you are going to operate some system, you have to be very careful with what should be your magnitude, what should be your phase limit. Okay, what should be your phase limit? Again, based on that we have to choose the operating range. Then what is the nature of this circuit? Okay, this circuit is again we'll call it this as some gain. Okay, say this circuit is providing gain of 1 for these frequencies. Again, beyond certain frequency the gain is getting decreased. That means what? Okay, again you are having input signal. That input signal frequency you can vary. Okay, so when the signal is having low frequency, the system is allowing that particular signal to reach the output. But once if you keep on increasing the signal frequency, it will not allow to the output. That is the idea, because the output is getting decreased. Output is getting decreased. That means it is allowing low frequency. It allows low frequency, okay, but not high frequency, but not high frequency. So this circuit nature will call it as a low pass filter. The circuit nature will call it as a low pass filter. Okay, so this circuit will act as a low pass filter because it allows the low frequencies but not the high frequencies. So the circuit nature will call it as a low pass filter. Okay, so next you take this exercise. Okay, suppose you reverse the component. Okay, so you put the capacitor here. Okay, then resistor here. Okay, this is Vi, this is V naught. Okay, then try to prove that this will act as a high pass filter. High pass filter, that means what? You are giving the input here, you are taking the output across R. You are taking the output across R. Okay, previously you took the output across C, now you are taking the output across R, then it will act as a high pass filter. Again, the circuit diagram may be like this also. In the exam, they may give like this also. Say, again, same structure I am taking. This is R, this is C. I am applying the input here. Okay, if I observe the output here, then what is the output? Again, if you compare these two diagram, both are same. If you compare these two diagram, both are same. Okay, again, this will act as a high pass filter. So whenever you have a RC network, if you take the output across C, then it will act as a low pass filter. If you take output across R, that will act as a high pass filter. High pass filter. Okay, just to try to prove this, then what will be the response for this one? The response will be, in the beginning the gain will be 0. It keeps on increasing, then after certain time the gain goes to 1. Okay, the gain goes to 1. Okay, this will be the magnitude response. Then what would be the phase response? Okay, previously we got the negative phase, now we'll get the positive phase. In the beginning the phase will be 0. Once if you keep on increasing the frequency, the phase will increase slowly, then finally the phase will reach plus 90 degree. Again, one more thing clear here, when you have a low pass filter, the phase is negative. For a low pass filter, phase is negative. This is another important concept. For a low pass filter, phase is negative, whereas for a high pass filter, whereas for a high pass filter, the phase will be phase is positive. This is another important observation. Okay, for a high pass filter, the phase is positive. Okay, and also one more observation we'll have here. Okay, see, once see here, you are getting 1 by 1 plus j omega rc. I think here you'll get the transfer function something like this: 1 plus j omega rc alone, h of omega. That means you are getting only the numerator. There you are getting only denominator. Okay, whenever you have a denominator, that we will call it as a poles. Okay, this will call it as a poles. Okay, numerator will call it as a 0. Okay, numerator will call it as a 0. That means what? Suppose when you have a multiple zeros and poles, if you have a multiple zeros and poles, okay, suppose if the poles is near to the origin, then that is low pass filter. If the 0 is near to the origin, then that is high pass filter. This and all we'll see in detail in the control system. Okay, so we'll proceed further. We'll take another example. Obtain the driving point impedance of the network. Obtain driving point impedance. Driving point impedance means simply the input impedance. Simply the input impedance of the network. Driving point impedance is same as the input impedance. Resistance. Okay, this is the network given. 1 ohm, 1 Faraday, 1 ohm, 1 farad. This is the network given. Then what is the driving point impedance? Okay, driving point impedance means is that input, is that of yes. Okay, is that yes. Okay, then you represent in the Laplace domain. Okay, 1 ohm, this is 1 by sc, that is simply 1 by s, and again this is 1 ohm, this is 1 by s. Okay, now again this is very simple. These are two uh, resistance parallel to each other, and these two resistance are serious to each other. Then finally they are in series combination. Okay, then first what is the z of s? That is simply 1 plus 1 by s. Again this parallel combination in series with this one, so again plus, then what is this parallel combination? That is again ab divided by a plus b, ab divided by a plus b, 1 plus 1 by s. Okay, then uh, 1 plus 1 by s, 1 by s plus 1. Okay, then finally s into s plus 1. Okay, s square plus 3s plus 1, s square plus 3. This is the driving point impedance. Okay, now what is the zs value? Zs is equal to s square 3s plus 1 divided by s into s plus 1. Okay, now suppose if I put s is equal to 0, what will be zs value? Definitely infinite. Or otherwise, if I put s is equal to -1, then what is zs value? Definitely that is infinite. Okay, then because I am putting s is equal to 0 or s is equal to -1, the function value goes to infinite. That's why these particular points are called poles of the transfer function. Okay, what is the definition of the poles? Poles is a point, once if you substitute that value, the function value will go to infinite. Okay, so again, so that's why s is equal to 0 comma -1 here called as a poles of the transfer function. Poles of the transfer function. Okay, the poles of the transfer function, but that is the zeros of the denominator. Okay, this is numerator, this is denominator. Okay, because how we got this one? Okay, we got this one just by doing equivalent with 0. So zeros of the denominator is the four poles of the transfer function. Zeros of the denominator is the poles of the transfer function. Similarly, zeros of the numerator is the zeros of the transfer function. So then just you calculate s square plus 3s plus 1 is, is equal to 0. Okay, then what will be the values of s? Okay, the s value. Sir, what is the value of this one? Can somebody calculate this? Hmm? Use the calculator. Yes. What is the value? You can use the calculator.
Sir,
சொல்லுங்க.
minus 0.335.
Minus 0.
335.
Okay, sir.
No, the minus 2.61.
Minus 2.61. Minus 2.61. Ah, okay, sir. Okay, now these points are called zeros of the transfer function. Zeros of the transfer function, and zeros of the transfer function is same as the zeros of the numerator. Okay, now just you plot it on the s plane. Suppose if I have a s plane like this, okay, then 0 is here, 1 0 is here, 1 0 is here, The another 0 is here at -1. Again, the pole is here. Pole will denote with cross mark, zeros with will denote with the round shape. Okay, then this is minus 0.33, and the another pole here is minus 2.61. Okay, once we took some network, okay, some network, RC network, again the order of the circuit is 2, because finally once if you write the differential equation, okay, here the second order equations are there, this is the second order network, but only with R and C, here there is no inductor. Okay, we took some RC network, then you observe the poles and zeros pattern, poles and zeros pattern, they are alternating. Okay, first zeros is there, next pole is there, first again zero, then poles, it's like that. And also they are on the real axis, they are on the negative real axis. Okay, and one more thing, why again it is near to the origin, the zero is there, near to the origin the zero is there. Okay, then how to identify that? Okay, once if you have a RC network, once if you have a RC network, the zero will be near to the origin. Okay, so the observation is zero will be near to the origin. Suppose if the network consists of, instead of capacitor, if the network consists of inductor, again you can replace this 1 Faraday with 1 Henry inductor. Then you calculate this Z of S. Then the pattern would be something opposite. Okay. It's like first poles will be there, next zeros will be there, then poles, then zeros. It will be like that. Okay, so this is some one simple observation. If you have a RC network, okay, near to the origin, what will be there? Near to the origin, zeros will be there. Near to the origin, zeros will be there. Okay, for RC network. For RL network, near to the origin, poles will be there. Okay, so similarly, again, the RC network is possible, RL network is possible, and also LC network possible, and also RLC network possible. Now we'll take the different network. Okay, then we'll see what is the nature. What is the nature of the sir, we made some mistake here, I think. Yes, we made a mistake in this diagram. See, the notation here is for a poles, we have to use cross mark. For zeros, we have to use the dot mark. So this is wrong. Okay, so it will be like this. Okay, in general, for poles, we'll use cross mark. For zeros, we'll use 0. Okay, then the poles will be here. Okay, poles 0 and one more poles at -1. Then where is 0? 0 is there here, minus 0.33, and one more 0 is there at minus 2.6. Okay, so whenever you have a RC network, the poles and zeros will be alternating, and also the near to the origin, and also the near to the origin, poles will be there. Near to the origin, poles will be there. Again, how to identify, how to remember this? How to remember this? Okay, suppose if the pole is near to the origin, what will be the phase, sir? Will it be negative or positive? The pole is near to the origin. Okay, you just compare it here. Don't switch on the cameras. If the pole is near to the origin, say for example, this is poles, this is near to the origin. If the pole is near to the origin, your angle will be negative. Okay, your angle will be negative. So, again, very simple. Say if you have a RC network, simply you remember about the capacitor. Okay, if it is capacitor, what is the nature, sir? 1 by S. Capacitor, what is the nature? 1 by S. Will it provide negative angle or positive angle? Capacitor will provide negative angle. Okay, capacitor means it will provide negative angle. Negative angle means always poles, because poles is in the denominator, that will provide negative angle. So that means poles has to be near to the origin. That is the simple way to remember. Okay, whenever you have a RC network, think about the capacitor. Capacitor means 1 by S. S means negative. Okay, if you need negative, then definitely poles has to be near to the origin. Again, these poles and zeros also will contribute some angle, but this will dominate. Okay, this will dominate. That is the idea. Okay, so next we'll take the various network. We'll see the nature. First, RC network. Already we took the RC network. Now we'll take the simple RC network. 1 ohm on Faraday. Then what is Z of S? Okay, what is Z of S? Z of S value is 1 plus 1 by S, that is S plus 1 divided by S. Which is near to the origins are poles or zeros? Anybody? Yes, anybody?
Poles.
Poles. Pole is near to origin. Pole is near to origin. Then how to denote this? Pole is at 0, 0 is at minus 1. Okay, this is the nature. Now what is the conclusion? The conclusion is pole and 0 on negative real axis. Negative real axis, and also alternatively placed, and also alternatively placed, but which one will be near to the origin? But the pole is near to the origin. Near to origin. Near to origin means in this case the pole is exactly at the 0 point. Sometime it may be like this. Okay, it may be like this also. Okay, if you take some other RC network, your pole 0 pattern may be like this. That's why we'll use the term near. Okay, in this case it is exactly at 0, but it is not necessary always to be at 0. It may be with some offset. It may be like this also. Okay, so but the pole is near to the origin or at the origin, near to the origin or at the origin. Then next network, RL network. RL network, 1 ohm, 1 Henry. Okay, then what is Z of S? Z of S value is 1 plus, yes. Z of S value is 1 plus, yes. Again, here this transfer function consists of only zeros. There is no poles. Okay, once if there is no poles, we'll assume that the pole is there at infinite. Okay, the pole is there at infinite. Now, what is the pattern? Okay, what is the pattern? The pattern is like this. 0. Again, there is no poles. We'll assume that the pole is at infinite. Suppose if you take a complicated network, that means if you have if you take more than one inductor, okay, then again there is a possibility that you'll get pole 0, again 0 poles, 0 poles, like that. Again, what I'm telling, when you take some other RL network, complicated network, the structure will be like this: first zeros, then poles, zeros, then poles. Okay, so here the 0 is near to the origin. That means uh, whenever 0 is near to the origin, then here 0 is near to origin. Okay, whenever 0 is near to the origin, what is another idea? The angle will be positive angle, whereas in the previous case the angle will be negative. Angle is negative. Angle is negative. In this case the angle is positive. So what is the conclusion? When you have a RL network, pole and 0 will be on negative real axis. Pole and 0 will be on negative real axis and also placed alternatively, but 0 is near to the origin, but 0 is near to origin. Okay, so once if this session is over, you can start with the same link. Okay, now 0 is near to the origin. Now we'll take another network, LC network. Okay, so you know that LC network is like a tank circuit. We'll see what is the nature of the LC network. L and C. Again, here there is no R, only we are taking the L and C. This is 1 Henry and 1 Farad. Okay, whenever you have a LC network, I already told you, when you have a LC network, if the inductor or capacitor is having some energy, the energy between the inductor and the capacitor will be keeps on transferring. First, the energy goes from capacitor to inductor, then energy comes from inductor to capacitor. Then in this process, once if you observe the output in any one of the element, either through inductor or capacitor, then that nature will be like a sinusoidal nature. That nature will be like a sinusoidal nature. Okay, then what is the impedance of this network? Okay, the Z of S, is equal to this is S, this is 1 by S, S plus 1 by S, then this is S square plus 1 divided by S, S square plus 1 divided by S. Okay, then what is the uh, pattern here? First 0 is there here, 0 is there at the origin, and again S square means what is this? S is equal to plus or minus J1. Okay, so again this is one pole plus J1 and then another pole is minus J1. That means finally the poles and zeros are on the imaginary axis. Okay, it is not on the real axis. Okay, it is on the